Cummins. I work for IBM. The particular part of IBM I work for is called the IBM Cloud Garage. And of course, when we say that, a lot of people say, what's a garage? What do you do? Explain. So we're like a startup within IBM. Our aim is to help customers adopt the cloud. We're consultants, so we go out to customer sites, we see what they're doing, we figure out whether it could be done better, we coach them along the road to cloud. So that's a lot of what I'm going to talk about today is experiences that we've had working with customers who are trying to take the most advantage of the cloud. I should say as well, we've got a network of about 14 garages, including one in Copenhagen, and the Copenhagen garage is hiring. So if you're local and you'd like a really cool opportunity, and if you're into test-driven development, extreme programming, lean startup, all that kind of thing, do reach out or Google IBM jobs. Because it's local in Copenhagen. But we also have Munich, London, Nice, Madrid. So if you're not in Copenhagen, we could also work with that. I want to start by giving a bit of a definition about cloud native. So how many people have a definition in your head of what cloud native is? So about half of the room, which I think is maybe 30, 40 hands. And I think what that means is that we've probably got 30 or 40 different definitions of cloud native in this room. Because one of the things about cloud native is it tends to be a lot of different things to a lot of people. It seems like an easy concept, but it does sort of get a bit muddied around the edges. I should say as well, I think one of the things that cloud native is really missing as a concept compared to, say, Java, is that it needs a mascot. So this is my attempt at a cloud native mascot. I think it's awesome. Everybody I've ever shown it to has sort of gone, stick to your day job. So, but see, it was like, if you imagined what a native of a cloud might look like, it might look a bit like that, but maybe a bit less like a Martian. Anyway, moving swiftly on to things that don't involve drawings of clouds. This talk started when I was reading Twitter, as one does, and I saw a tweet by Daniel Bryant, who spoke earlier today. And in general, if Daniel says it, it's right. But I looked at this tweet, and I thought, I'm not really sure about this. And you can't really see what it was that I was concerned about, but if I make it a bit bigger, you probably can, which is that there's this positioning of cloud native and this definition of cloud native as something that was on a spectrum from SOA to microservices to cloud native. So when you had SOA, you had smart pipes and dumb endpoints. Then you progressed to microservices. Everything was a lot better. You had smart endpoints and dumb pipes. And then you got even better, and you progressed to cloud native, and you had a smart platform and dumb services. And I thought, to me, that just doesn't feel like what I do. That doesn't feel like the things I'm telling clients to do in order to become cloud native. That doesn't mean it's a wrong definition. It just means it's not right for me. We say that our team builds cloud native apps, and yet often we don't have microservices. So how does that even work? Are we wrong? Well, to be fair, the article that this came from, one of the reasons it was talking about cloud native as an evolution of microservices was it was an article about microservices. So of course, if your article's about microservices, then it makes sense to talk about cloud native as a form or as a progression of microservices. And it's a really good article. So even though I was a bit concerned about that diagram, for me, the article as a whole is really good, and you should all go off and read it. It's by Bilge Nibrium, who works for Red Hat. And again, if you're talking about microservices, then that makes sense in that context. But of course, it's not just in that one article about microservices where we talk about cloud native and microservices as if they're pretty similar things. The Cloud Native Computing Foundation have this very long definition for cloud native computing, which I won't read out, but the key things in it are they say it's microservices, containers, and dynamically orchestrated. Well, I like the dynamically orchestrated part, but the other two, I'm just a bit less sure about. But then that puts me in this really weird position, which is that I'm here standing in front of lots of you at GOTO Copenhagen, and I'm saying, the Cloud Native Computing Foundation, what do they know about Cloud Native, right? I'm sure I know way more than a whole foundation that's been set up that my employer sponsors, whose name is the Cloud Native Computing Foundation. And so I want to try and figure out, well, why is my definition so different from the definition of the people who were supposed to know about Cloud Native? And in the front row here as well, there's 4 people who all have Cloud Native guru top. So I'm a bit afraid that at some point, there's going to be a rush to the stage, and you're going to come and tell me that I do have it wrong, and I need to stop talking about Cloud Native because really I've misunderstood something. I was a bit alarmed as well, because I was reading Twitter before this talk, as one does, and there's a tweet from Casper who's saying, if you're attending GOTO Copenhagen and want to discuss Cloud Native Foundation technology, please, give me a personal message or find me at the venue in the next couple of days. And I thought, oh, well, I'm planning to discuss it in about an hour, but I'm going to discuss it in front of quite a few people, and I don't have time to talk to you first, so I hope what I say is okay. And then eventually I worked out he wasn't actually wanting people to get permission to talk about Cloud Native. He just was offering to discuss Cloud Native. So if after this talk you're very upset, you can go and talk to him. You can say, I saw this terrible talk, and they really didn't understand Cloud Native at all. Let's have a chat, and you can tell me what the proper definition is. To be fair as well, although I was a little bit worried about the microservices and the containers part in the Cloud Native Computing Foundation, the last part of that sentence is talking about the reasons why you'd want to do Cloud Native. And this, I think, is absolutely right, because the reason why you'd want to do it is you want to build great products faster. And to me, that's the most important thing about Cloud Native, is the why. Or another way of thinking about that is, well, what problem are we actually trying to solve? And the problem probably isn't, I need to use more containers. If you're trying to polish your CV, if you're looking for new employment, if you're trying to negotiate a new pay rise, maybe the problem you're trying to solve is, I need more containers, I need more Kubernetes, I need more something like that. But in general, my CV looks dull isn't really a good reason to go Cloud Native. There has to be some kind of underlying business problem or business requirement that's going to move you in that direction. And to think about what that requirement might be, it's helpful to step back from Cloud Native and think, well, why cloud? When we started talking about cloud and thinking about cloud, and I'm old enough to remember the shift in the industry from not cloud to cloud, we really thought about it like a utility. And we thought there's all these things like electricity that we're no longer generating in-house, because that would be financially really inefficient and it wouldn't actually get us anything. We want to outsource these. And our computational power is the same thing. We want to outsource that, and it's going to be way cheaper. We're going to save a lot of money. And in particular, the reason it's going to be so much cheaper it's partly that people who maintain these systems for a living are probably going to be able to do it more efficiently and more effectively than we can. But it's also because we're going to have more elasticity. And what that means is that if on Black Friday I get a ton of traffic, but the rest of the year I don't get very much traffic, in order to support that Black Friday traffic, I have to have provisioned the maximum capacity. And then the rest of the year, I'm paying for all of this capacity that I don't need, all of this hardware, maybe, if I don't turn it off, the electricity. So instead, let's have something where I only pay for what I use, this utility model of computing. There's another big advantage that we saw when we moved to the cloud, and that was the promise of speed. And by this, I don't really mean hardware speed, although we do see a little bit of that as well. So we're now starting to see GPUs for machine learning and for data processing in data centers. And you wouldn't necessarily want that kind of hardware, certainly not in the quantities that you can get it in the cloud in your local data centers. And we're also starting to see even more exotic hardware as well that would actually just be impossible to have locally. So for example, IBM make quantum computers available on the cloud. There's only a handful of quantum computers available in the world. So you're not going to have one in a local data center, and they need to be cooled to about 0.4 Kelvin, which is colder than the space between the stars. So you're unlikely to achieve that kind of temperature in a local data center unless you're really good at refrigeration. But the speed that the business was thinking about with the cloud was more speed from when we write our code to when we get it to our customer. Because it used to be, you'd have to do this really tedious process, and you'd cut your release, and then you'd have to send it off to Dublin, and they'd actually print your software onto CDs, which seems incredibly quaint now, and that whole process would take a long time. You wouldn't want to do it very often because it was so irritating, and so you'd only release software maybe once every year or once every 2 years. With the promise of the cloud was, wow, because the cost of getting our software to a customer is so much lower, we can do it more often, we can be more responsive to the customer. We're also seeing some more exotic capabilities in the cloud. So for example, we've got Watson on the cloud. There's TensorFlow, there's all of these things that would be pretty complicated to run locally, but instead you can just take advantage of those services, pull a whole bunch of different services together into an application, and make something a lot more interesting than you could do locally. So that all sounds amazing, right? So why cloud native? Why wasn't cloud good enough? Well, we thought about cloud like electricity. It was this utility that we could all take advantage of. But what in fact happened was that a lot of us moved to the cloud, and my clickers just died, which is exciting. It's the punchline. It's building up the suspense. We moved to the cloud, and right, hopefully this one will work. Otherwise, we'll never find out. Hooray! So we moved to the cloud, and we got electrocuted. So that you never want a technical failure, but the slide about technical failure is probably the right point to have the technical failure. So a lot of us found that things that had worked really great on-prem were horrible on the cloud. We were losing data, we were getting outages, we just couldn't even stand it up in the first place. What was going on? Well, we eventually worked out a bunch of patterns that had made a lot of sense when we were running in a data center that made no sense at all in the cloud. And these were things like log management. It used to be that the right thing to do was to have about 6 different files for your logs, and you'd put messages of this type into this file and messages of this type into this file, and you'd have different granularities in the different files, and then you'd roll your files, and then you'd copy them to a different place on the file system. And we had all of this elaborate infrastructure for doing the right thing to our logs. And in the cloud, what would happen was we'd do all of these things to our logs. Our virtual machine would die, and then we'd never be able to get those logs. So we had no way of figuring out what had caused the demise of that container because it was dead. So instead, we had to sort of roll back, and we had to say, oh no, we need to treat logs like event streams. Just putting it to standard out is fine. You don't need to do anything harder than that. And if you do anything harder than that, actually, you're going to regret it. So these got encoded as the 12 factors. So some people say, oh, well, the 12 factors aren't the exact right 12 factors. They were what you need to make an application run on Heroku Cloud, and some of them aren't quite right, and there's some others that you need. But basically, they were a really good start for how to write an application to run on the cloud so you don't get electrocuted. And one really important thing with the 12 factors is that there's not really anything in it about microservices. And yet, to me, it feels like a really good definition of cloud native. And most of the stuff in the 12 factors is stuff like being idempotent on restart. And so cloud native, I think, should be much more about being 12-factor-ish and much less about being microservices. And if it has to be a synonym for anything, really, it should be idempotent. And if anything needs a synonym, it's idempotent, right? Because idempotent isn't much fun to say. It's not much fun for me to say as a native speaker. I think it's probably even less fun to say if you're not a native English speaker. So where do containers fit in all of this? Because nothing in the 12 factors is anything about containers. Well, I think containers have been such a transformative technology. There's a whole bunch of things that were really hard before that containers made simple. There was all of this complexity that we had to deal with in order to stand something up, in order to take a piece of software and make it usable for us, that containers just solved. So that's really good. But the key thing with containers is that containers are good, but it's not a competition to see how many containers you can have. It's not like if I have one container, I'm doing well. If I have 10 containers, I'm doing great. And if I have 60 containers, I'll get a raise. You know, their power doesn't increase with their number. And in particular, thinking about microservices, you need a modular application in order to scale, for sure. But you don't need HTTP communication between the parts of your application in order to be cloud native if you have all of these other characteristics. So who knows the story of the Space Pencil? Couple of hands. So this is a classic story about complexity. And the story is that in the dawn of the space race, NASA spent millions of dollars inventing this pen that would write in space. And the reason it needed all that engineering is because in space there's no gravity. Normal ballpoint pens work by gravity forcing the ink down. If there's no gravity, then you have to have a little pressurized canister to force the ink down, and it all becomes quite expensive. And the story is that the Russians did not spend millions of dollars inventing a space pen. Instead, the Russians just used a pencil to write in space. And the moral of the story is that complexity adds expense. And in particular, unnecessary complexity, like using a space pen when you could just use a pencil, adds unnecessary expense. Now, it turns out the story is wrong in pretty much every single part of it. So the first thing that's wrong is that actually, both at the very start of space exploration, both NASA and the Russians used pencils. That was all they had, they used pencils. But there was a financial scandal about NASA and the expense of their writing things, because their space pencils cost about $130 each, which in 1960s money is a huge amount to spend on a pencil when it's just a pencil. The space pen wasn't actually developed by NASA. It was developed by an independent company, because having been bitten by all of the outcry over the $130 space pencils, there was no way that NASA were going to spend any more money on developing anything to do with writing in space. So it was an independent company, the Fisher Space Pen Company, that did the space pen. But actually, they spent about $1 million to develop it, but once they worked out their economic model, they actually sold it really cheaply. So they sold it for about $2. So the space pencil is about 60 times more expensive than the space pen. And there's another interesting thing about pencils in space, which is that if you write with a pencil, you probably don't even notice it, but you leave sort of a fine trail of graphite on the paper. Some of it's stuck to the paper, and some of it's just floating. Well, it's sat on the paper, and it's not causing any harm because you're on Earth. If you're on space, it doesn't just sit on the paper. It sort of floats up. And then you breathe it in and that kind of thing, and it causes all sorts of problems. If you accidentally break the nib and you get a larger piece of graphite, that causes even more problems, because then it can go into an eye and cause eye damage, all sorts of things. So it turns out that pencils in space are a really, really bad idea. Another problem with pencils in space is that they're flammable. NASA tends to avoid putting flammable things where it doesn't have to. So this morning in Casey's talk, he made a really good distinction between accidental complexity and essential complexity. So accidental complexity is the kind of complexity that arises, it doesn't need to be there, but it just arises because we're all busy people, we're all human, we're all dealing with multiple conflicting demands, and so this complexity just sneaks in. Essential complexity is the kind of complexity that really has to be there in order to meet your business goals. For example, if you want to have high availability, you need to have some redundancy in your system. That redundancy makes it harder to manage. You need to figure out how to push your updates to 2 places. But you can't just go through your system and say, well, let's get rid of all these redundant servers. Our system will be so much more simple, because your system will be more simple, but it will also be much less useful. So it has to be there. And Casey was talking about how you have this idea of, oh, well, let's not put complexity where it doesn't need to go, and thinking, well, who would put complexity where it doesn't need to go? His optimistic assumption was that no one would. I think if you're working on your CV, you do actually put complexity where it doesn't need to go, because we do have this fear of missing out in terms of technology, and we do have this idea that if everyone else is using some technology, we should do it as well. And that's why you see a lot of businesses copying the Netflix model when they don't have the same requirements and constraints as Netflix, and you end up with these architectures that perhaps aren't the right kind of architecture, but they make everybody involved feel like they're doing something really interesting and challenging. So stepping back again to containers. I defined cloud native, sort of, and I want to define containers as well, because I've been talking about whether cloud native or whether containers fit in the definition of cloud native or not. And I think in order to have that conversation sensibly, you do kind of have to have a definition of what is a container. So way back when, we all started with bare metal servers. Those, you still can do those, you still can get those. And even on the cloud, actually, you can still have bare metal. So for example, we have some bare metal servers that give really good performance, but at a cost, so it depends what the requirements are. But we quickly realized that bare metal servers were a pretty inefficient way to operate cloud services, so we went to virtual machines. Those were amazing. We could fit lots of them on a single bare metal. We could pick them up and carry them around. They were a revolution. Containers were even more of a revolution because containers were so lightweight. I think we perhaps all got a little bit excited about containers, and so I've seen containers used in places where they're not appropriate. So for example, I've seen containers used as a zip file. A container is a really bad way of making a zip file because all of the caching, which is one of the benefits of containers, you lose, and so then it just ends up being an expensive way to do a zip file. But if all you have is a hammer, if all you have is a container, then your zip files look like nails or something. But the other thing to note about containers as well is they've been around for a while. It's an old Linux concept. They, of course, became super popular with Docker. They're not just Docker, and now I think we all are quite comfortable with that idea. But even before Docker, they weren't just Docker. So Cloud Foundry, for example, I'm a big fan of Cloud Foundry. I think the industry is going towards Kubernetes, but Cloud Foundry has a lot to offer. So the developer experience, for example, with Cloud Foundry is superior to Kubernetes at the moment. Now, of course, we have this tribalism between containers and functions. So we have the containers people and the functions people, and the serverless people. Containers people say there's no such thing as serverless, and then the functions people say, yes, but we scale way better, and we're way better in lots of ways. Functions, I think, do create their own complexity challenges. I worry sometimes about the testability of these systems because each individual component is very testable, but the emergent behavior is not necessarily so testable. And so the units that you're testing are smaller, which may be a good thing or may not be. But container functions do have some real advantages over containers in terms of their scalability characteristics, in terms of how you can spin them up and get really good, finely grained scalability, deployability, that kind of thing. They also have some problems. We see, for example, that there's a lot of constraints that get put on the functions by the runtime. So for example, if your dependencies go over a certain size, that can be a problem. If your startup time is quite long, that can be a problem. And so we are seeing a little bit of a rollback as well to, well, functions are good for this kind of application. Containers are good for this kind of application. If I've got really complex dependencies, maybe I want to be using a container, but I'd quite like those scalability characteristics of the functions. And so then we get funtainers. And so a funtainer, it's not as fun as it sounds. That is a combination of function and container, and if you combine those two, then you get funtainers. I have to say, I think funtainers technically make a lot of sense because they take the best of both worlds, but they do have a problem, which is that I read an article about funtainers, and I thought, oh, this sounds really good. I want to learn more. I want to see if this is appropriate for me. So I Googled FunTanners, and for 2 pages of Google results, this is all I had. So if a technology can't be Googled, it's never going to take off. So I said FunTanners weren't as fun as they sounded. Actually, they kind of are, right? Because it's all of the fun of containers, but without the hassle of having to manage Kubernetes, which is pretty much the dream, right? But going back to cloud native was a thing way before Docker popularized the container idea. So containers and Docker were sort of around 2013. Microservices as an architectural pattern really started to be talked about in 2011, but we started talking about cloud native in 2010. So to me, this proves that cloud native is about more than just microservices and containers. The alternative interpretation is that it just proves I'm really old-fashioned and that the definition has changed and I haven't kept up because I've stuck to the first definition that I saw. But in that blog post that I just showed, so cloud native really came from both the Netflix community and also from Paul Fremantle. And Paul Fremantle's definition, which seems really intuitive to me, is something that behaves well on the cloud. And then the follow-on from that is experience shows in order to behave well on the cloud, it has to be written for the cloud. Otherwise, it's just going to behave disgustingly on the cloud. But so far, I've been talking for quite a long time about containers, what is a container, should we use containers, microservices, and all of that is nothing to do with culture. So that's all how we run our application, not what's in the application. But in terms of the business impact of what we do, in terms of the user impact of what we do, in terms of our ability to change the world, that's all about what's in the application, not just the mechanism that we use to run it. And so going back to these goals that we had with cloud native, the goal was speed. But what's the point? Slow. So we've got the speed, but then we're not taking advantage of it. What's the point of having all this speed, but then just sending the same old things that you've always been sending to the market, but doing it a little bit faster? And what's the point of being able to respond to the market if you don't respond to the market? And what's the point of an architecture that can go faster if you're not actually going faster? So there's this anti-pattern that we see, which is having a microservices architecture, but not actually having the architectural characteristics apart from the microservices that enable you to go faster, and not having your culture that enables you to go faster. And so then that leads to cloud native failure. So this is what happens to the cloud native mascot when things go wrong. And this is all based on stuff I've seen working with customers. And I think sometimes you look at the list and you say, well, this is also terrible. I'd never write any applications like that. And if so, that's really good. That's in a good place. I think sometimes others look at it and say, oh, I do all of it that way because it's hard to change. And that's also true. These things, everybody gets to these points with good intentions. So the first anti-pattern is the microservice failure. So I was sort of looking at a new code base, and I realized that the domain model was quite complex. It had about 20 classes, it had 70 fields, and each microservice needed to use pretty much that whole model. And so they knew that with microservices, you weren't just supposed to have a shared object library and have everybody reference that, because then you've got this coupling. So instead, what they did was they cut and pasted the code between each microservice in order to not have the coupling. But it was still just as coupled, right? Because every time a field name changed in one microservice, every other microservice broke. And so, the dream with microservices is that you've got your microservices and you've got your domain model, and your domain model is just as decoupled as your microservices, and each domain maps really neatly to a microservice. But what had happened here was basically we had this huge domain model, and then we'd split up loads of microservices, but they weren't decoupled. And so then that leads to the next problem, which is every time they changed code, something broke. And the reason for this was because even though they had all the HTTP communication between their microservices, basically what they had was a distributed monolith. And another way of thinking about that is cloud-native spaghetti. So if you take your pile of spaghetti and you put it up, this is from Cloudy with a Chance of Meatballs, by the way. And I don't think they were intending to make a metaphor for cloud-native computing, but it's hard to imagine a better one in some ways. Because you take your spaghetti, you put it up into the cloud, and it doesn't get any better. It just gets more violent when it goes wrong. So just because a container runs across lots of containers, or just because a system runs across lots of containers, that doesn't mean it's decoupled. It just means it's a lot harder to debug and a lot harder to manage that coupling. So this is the Mars Explorer, which is a rather sad NASA story. So this is what it actually looks like. I love this, because if you look at it, you can see it basically looks like it's made out of a tumble dryer, some bin bags, and some sellotape. So like those pipes there really look, I'm sure I've got the identical ones in my tumble dryer. And like that really, I've got bin bags that look like that. And then those little things there look exactly like sellotape. So the Mars Explorer did not have a happy end. I don't think it was because it was made out of a tumble dryer that they repurposed. It was a more subtle problem than that. So the fate of the Mars Explorer was that it crashed into Mars. And the reason for it, does anybody remember the reason? Casey at the back remembers. Yeah, exactly that. It was metric and imperial. So we had the Mars Explorer that used metric units. We had a control unit on the ground that used imperial units. And in this case, the system was very distributed. It was distributed all the way to Mars. And distributing did not help, because the problem was fundamentally a contract one. When they'd gone to their supplier and got that supplier to just write that one part of the system, they hadn't really specified carefully enough their assumptions about the units. Everything seemed to work, but it actually, they accumulated a series of small errors, and the effect of that was that it crashed into the sun, or it crashed into Mars. So the moral there really is that with microservices, you absolutely need consumer-driven contract tests, because otherwise there's a whole bunch of assumptions that you'll have in one team that the other team doesn't know about. You'll make changes in one team and the other team won't know about them, and then you get problems. And of course, a key thing with your consumer-driven contract tests is they need to be automated. So if I go to a team and they say, our tests aren't automated, what I hear is, we have no idea if our code works, which is kind of a terrifying thing to hear. Because if you don't know if your code works, odds are at least some of it doesn't work. Because even if everybody on that team is perfect, systems are going to behave in unexpected ways. And documentation for dependencies can be wrong. Documentation updates or dependency updates, they can change behavior. You may be relying in a bug on a dependency. When that dependency bug gets fixed, things go wrong. And so then the effect of all of this is that you get these bugs. So with the Mars Explorer, when they did the analysis of it, they had this rather sad statement that said, had we done end-to-end testing, we believe this error would have been caught. So they had their components, each component was well tested, but because the system as a whole wasn't tested together, the error didn't get caught. And so without those tests, this leads to a kind of a business paralysis, which can be quite controlled or it can be quite uncontrolled. But either way, what the business will say is, we have no idea if our software works. So we're going to do a long UAT phase at the end to make sure it works. And we certainly can't ship until we go through that UAT phase. So basically, the dream of Agile is we should be able to ship at any point, but we can't ship because we don't know if things work, so we can't ship. With microservices, because they're supposed to be independently deployable, you really need, you need your contract tests, and you also need automated integration tests. And the thing with those is that there's no point in having those tests unless people look at them. So I've also gone into teams and I've said, okay, where's your build? Where's your build status? I've eventually found it, and it's been red. And I've said, oh, the build's red. And they've said, oh, is it? So there's no. If a build fails and no one's seen it, it's like a tree in the forest. Someone has to know that a build fails for that build to be giving value, and really that should be passive. It shouldn't. I've sometimes found that there's one person on a team who ends up being sort of the build cop, and so when the build fails, they'll notice it and then they'll go and they'll tell Bob off. But that's not really a good way of doing it. It's got to be that Bob finds out in a passive way. So if you've only got one build, having a traffic light or something like that, a siren of shame, is good. If you've got more builds, then probably something like a build radiator is going to be a better option. But you've got to have something. Another thing I've sometimes heard is I've said, oh, this build is broken, and they've said, yeah, it's been broken for weeks. Which is so sad, because this is the classic broken window problem, that once people get used to seeing something as red, they no longer have any urge to fix it. They get used to that thing as red, and this can lead to some quite serious problems. So this isn't a NASA story. This is a Russian space agency story. And so the lesson is how to brick a space probe, but you could also think of it as how to get fired from the Russian space agency. Which is that they had, this was back in the 80s, and they didn't have what we would think of as automated tests, but they had an automated linter. And so code would go through it, and then they'd discover problems. And it was all assembly code, so it was pretty tough to eyeball that code and discover problems. And this hapless engineer made a small error, and he put an extra hyphen in. And unfortunately, the automated checks weren't working, and he really wanted to get that update out. So he said, well, I'm sure my code is good enough. I'll just bypass the automated checks, because the automated check was broken. And the effect of all that was that it bricked the space probe, because it happened by unfortunate coincidence that the effect of that hyphen was to change his command to the command to turn off the charging mechanism on the space probe. So it had these fins that would sort of follow the sun. He turned off the fins, and so then it was just sort of sat there floating in space, and then eventually it ran out of power, and there was nothing that could be done. So that was the end of that space probe. We see a lot of cases where there's the ability to move faster, but the processes that we put in place to prevent accidents aren't keeping up. So in this case, it was a technical failure. But we see a lot of process failures as well. So one of the first projects I did with a client, they really wanted to become more cloud native and take advantage of the cloud. And so we got their application out, we got it to it was running, customers were using it, we were really pleased until they came to us and said, well, we've scheduled your architecture review board. And we said, but we've shipped it, we're done, we're off the project, it's done. And they had this process that had been put in place to catch problems, but the timelines were just so incompatible that this process made no sense, but we still had to go through it. And with the Mars Explorer, they had sort of it was a different process problem, but they did have this sort of a process that instead of helping things, hurt things. Because the engineers who were responsible for the navigation, they could see that something wasn't quite right. So the way it worked was that they would make an adjustment, and then a while later they'd check to see where it was, and it was never quite where they expected it to be. So they warned, well, something's wrong here. But they didn't fill in the right form. And because they didn't fill in the right form, nothing was done, and then they lost the space probe. So really, it has to be thinking, does this process add value? If the process doesn't add value, get rid of it. That doesn't mean you don't want to be rigorous. You want to be really rigorous, but it needs to be a different kind of rigor. So I'm a big fan of extreme programming. I think that's the right kind of rigor. It's hard to do, but it's well suited for the cloud. So test-driven development, making sure that you've got those tests, making sure that they have the ability to fail, making sure that there's asserts in the tests rather than just having 100% coverage and no asserts. Pair programming, so rather than doing a code review that's possibly offset by some amount of time and it's too late to catch problems, catch them at the time with pair programming. And it's all really optimized for feedback. And that, again, that's the promise of the cloud, is that feedback. So we see a lot of businesses who have the technical ability to get the feedback, but they cut themselves off it. So we'll discover that a feature that we thought would be a really good idea, as we start going through, we realize, actually, this isn't going to add any value. Let's not do it. This is particularly a problem when we're doing contracting, because contracts tend to be not very flexible, but we'll have this problem where something's in the plan. So even though everybody knows we shouldn't do it, there's a reluctance to change the plan. And we see the same thing in the other direction as well, where we have this great new idea, but because it's not in the plan, we stick to the plan. So the Titanic is, of course, a classic microservices analogy, because if you think about Titanic, you think about bulkheads. If you think about microservices, you think about bulkheads. The Titanic did have bulkheads. They had made an interesting optimization with their bulkheads, which is that instead of the bulkheads reaching all the way to the top, they stopped about 1.5 feet below the top. And what that meant is that once things started to go more off-plan than they had anticipated, it tipped too much, and the water flowed over the top of the bulkheads, and then it had a really rapid failure once it got to a certain failure point. But the main problem with the Titanic, actually, it wasn't really a bulkhead optimization. You know, it was kind of a sensible optimization that they'd made with the information that they had. And the main problem with the Titanic was a size problem. So the Titanic was the largest ship of its day. It was about 4 city blocks long. And that was mostly fine, except when navigating through iceberg fields, they didn't have any radar, they didn't have anything like that. So the normal mechanism for navigating through an iceberg field was that you'd have a lookout. When the lookout would see an iceberg, it would say, oh, we need to go to the left, look, there's an iceberg up ahead, and everybody would adjust. With the Titanic, the lookout saw the iceberg that took the ship down by raking down the side of the ship. But because the ship was so big, it wasn't nimble enough to avoid it. And so then, of course, there was an enormous loss of life. So I've seen a few references to Hidden Figures already today. How many of you have seen Hidden Figures? Only a small number of hands. OK, so for everybody else, you must go and watch Hidden Figures. It is such a good film. It's a feel-good film about racism and the Cold War and mathematics. And if that doesn't sell it, then I don't know what would. So the starting point for Hidden Figures is that it's the dawn of the space race. Really, pre-computers, or computers are just starting. So this is the computer room. And the computer isn't that blue typewriter at the front. The computer is the people. And NASA are aware that they're losing the space race. They can see that the Russians are getting things into space, and they're not. They need to figure out how to modernize. They need to figure out how to accelerate their space program. Technology is, of course, the obvious way to do this. So they bring in an IBM computer, but they have a couple of challenges with it. So let me just make sure that this works.
One, you make it two, make it double, okay? You gotta get it. Just make it happen now.
No one thought to measure these things?
I'm afraid not, sir. Well, would you like us to stop?
So that's the hallway.
No.
The computer's in the hallway because it can't get into the room.
No, just keep going. In fact, use the big hammer.
Yes, sir. Come on, use a big hammer. You heard the man. Let's go.
And so that final shot, she then goes on to teach the human computers Fortran, and then they become the Fortran programming team. So there's the computer when they finally break down the door and get it in. And I think the thing that I find interesting about this isn't that there was a plan problem, that they hadn't anticipated how big the computer was when they built the building. Because, of course, when they built the building, computers didn't exist. They couldn't possibly have anticipated how big an IBM mainframe was when they built that building. So the plan was perfectly correct. IBM couldn't have made that computer any smaller because it was the first transistor-based computer. They were big. And so the key thing wasn't that there was a plan problem. The key thing was in how they responded to the plan problem, which was in this case that they showed the agility to use a bigger hammer to knock down the wall. But often we find that we're not responding to these changes, and we want everything to be perfect. And we don't want to knock down the wall. We don't want to make these compromises. And really, that means we're depriving ourselves of the opportunity for feedback. So you would never, ever, ever drive a car, by going like this and not seeing, because it's that feedback, that knowing what's in front of you is really critical. And often when we see engineering problems, the underlying cause was a lack of feedback, either because of a lack of tooling or because of decisions that had been made, or because of fundamental engineering constraints. So with the Mars Explorer, one of the reasons that they had problems was that most of the time they couldn't see the Explorer. And so they'd have to sort of make a course correction and say, well, I think if you go, power the thruster for 2 seconds, then you should end up roughly where you need to be. But they couldn't actually see it, and that was why they didn't realize that it was so close to Mars until it was too late. And feedback, it's really good business. I've been using the word business a lot. I'm an engineer, so feedback is really good engineering as well. It's so important. And we talk a lot about an MVP now, and the aim of an MVP is to get feedback. It's to figure out what your hypothesis is and do the minimum that you need to do in order to figure out if that hypothesis is right or not. And that can be so uncomfortable because we all want things to be perfect, and we all want to have something be right. And so there's a saying about an MVP, if you're not embarrassed by your first release, it was too late. So if you're not doing it right, if there's not some things in your MVP that you look at and you say, oh, I hope nobody sees that, because it's just, I really wanted to polish that nose cone and I haven't. And the goal of an MVP is to do an experiment. And the point of an experiment is that you don't know what's going to happen. If you knew what was going to happen, it wouldn't be an experiment, it would just be business as usual. And then for our stakeholders, that can be really uncomfortable, because when we say, I'm going to do this, and it might not work, then that actually means there is a good chance, I'm doing something that can invoke failure. That's scary. But it's important as well. We have to do that kind of experimentation, and we have to learn from the world around us. So with the Titanic, when they found the wreckage of the Titanic, they were a bit surprised and confused, because most of it was there, and the staircase wasn't there. And they could tell from the photos of the Titanic and from the plans, it had a staircase when it set sail, so how could it not have a staircase? And they thought, oh, well, maybe it was because it was wood, and the wood rotted. But a lot of the other wood was still there. And in the end, they discovered what happened to the staircase because of the Titanic film, because James Cameron recreated the Titanic so faithfully that it was actually like a retroactive experiment about the Titanic, and they discovered lots of things. And one of it was the behavior of the staircase. Because even though the staircase was nailed down, when they flooded the ship, what happened was the staircase was buoyant enough that it ripped off its anchors, and it sort of fired up through the roof of the Titanic and floated away, and then it got eaten. And so really, users are like staircases. We think we understand how staircases work, but then things get weird. And we think we understand what our users want, but they're just weird. They're going to do really weird things. When SMSs were introduced, the phone companies thought, well, this is a nice little side feature, but people might use it a little bit. And they weren't expecting at all the complete shift in behavior that happened from people wanting to talk by voice to people realizing actually they hated talking on the phone, and they'd only done it because there was no alternative. As soon as we had an alternative with SMSs, people started using SMSs. And so when we do our systems, we need to optimize so that when, if we're in charge of the SMS infrastructure and it takes off, that we can adjust. And we need to optimize for recovery as well. So when things go right, we need to adjust. When things go wrong, we need to adjust. So the problem with this space probe was that it was so unrecoverable. Once it had lost power, there was nothing that they could do to salvage that system. So if you think about sort of a spectrum of recoverability, at one end is something has gone wrong, my system is bricked. There is nothing that will ever make that system work again. A bit better, but only a bit better, is a thing where you have lots of handoffs. And so you have to ask for permission to fix a system, and you possibly have to ask for permission from multiple people to fix a system. Well, that's going to take a really long time, and it's going to be really slow and really annoying. If only one person has to intervene, well, that's a lot better, but it's still going to be pretty bad. If the recovery is fast, but data is lost, well, that's better, but users aren't exactly going to be delighted. And of course, the best is that you're back in milliseconds and there was no data loss. And so that's the cloud-native dream. It's not just about what we put in it, it's about how we handle it if things go wrong. And if we get enough automation, and if we get enough item potency, then we can get that situation where we've got the business recoverability and the technical recoverability. But the business recoverability is important as well because users are like staircases. They're going to do weird things. And so I've talked a lot about recoverability, and I've talked a lot about speed. And speed, I think, is one of the most important parts, not just because it's satisfying. So as engineers, if we make something and it doesn't go out, and it just takes forever to go out, and there's loads of handoffs, that's really demoralizing. You know, I hate that personally. I know my teams hate it when what we do doesn't go out. But fast is also really good for business. So we get stressed when there's late requirements changes, but we should be happy because it's a competitive advantage if we get a late change in requirements because we know more. So more feedback means more accuracy. And the cloud, there was all sorts of tedious stuff we had to do until we had the cloud. And so cloud native should feel the same. Cloud native should feel that there's a whole bunch of tedious stuff that we used to have to do that we don't have to do anymore. And that should feel good. So with that, I will stop. Please rate the sessions. Please rate all the sessions. And thank you very much.